Welcome back for the last talk of the day. Now we have a workshop lined up with Tomasz and Hernando from Parity Technologies talking about bridging substrate-based chains to Polkadot. Interoperability between networks has always been core to Polkadot's value proposition. In this developer workshop, you will learn how to integrate your standalone substrate chain into the Polkadot ecosystem using a bridge. As a part of this journey, you will learn how to use these bridge building blocks to enable communication between a parachain and sovereign chain built using Substrate. More concretely, this means integrating our on-chain Grandpa Light client and bridge messaging pallet. We'll also show you how to use messaging to perform an over-the-bridge token transfer. By the end of this workshop, you should be equipped with tools to connect your sovereign Substrate chain to one of the Polkadot parachains and leverage the vast Polkadot ecosystem. Tomasz and Hernando, take it away.
Everyone. So thanks for the intro, Peter. And today what we're going to be talking about, again, is bridging Substrate. And in particular, talk about the path that we're taking here at Parity to bridge Kusama and Polkadot. So first, a little bit of an intro about who we are. So I'm Hernando. I'm a developer at Parity Technologies. I'm based out of Toronto, Canada. So if you're Canadian, say hi in the chat. And I started working at Parity a couple years ago, initially on the Ethereum client with Tomasz. But now I found myself working on bridges.
And I'm Tomasz Drwięga. I'm Parity's OG core developer. I worked on the Ethereum client initially, later on Substrate and Polkadot. And around a year ago, we started together with Hernando and the rest of the team to work on bridging efforts.
Yeah, so a little bit about the rest of the team. I want to give them a shout out. So Slava is, I think, the biggest contributor to the code base. Andreas works on some of the consensus stuff, and Hector is really leading the UI effort. And then I also want to give a shout out to the team behind Decoded. Like a conference like this takes so much longer than just a week to prep. So I just want to, commend them for their efforts on putting such a good event together. All right, so a little bit of a plan for the workshop. First, we're going to give you some motivation and an overview of what we're doing here at Parity. Then we're going to show you a UI demo of cross-chain transfer. Then we're going to do a little bit of a deep dive in some of the different components that we built. And then at the end, if we have time, we'll do a question and answer session. So interoperability. This is really the name of the game for Polkadot. And there are a couple of different ways to plug into, this interoperability story in the Polkadot ecosystem. So at the core of it all is Substrate. And for those of you that don't know, Substrate is a generic blockchain building framework that we've developed here at Parity Technologies. And from here, you can either build a standalone Substrate chain, which can connect to Polkadot via a bridge, or you can plug in directly through a parachain. And Tomasz is going to tell us a little bit more about the trade-offs between each of these interoperability decisions.
Yeah, as Hernando mentioned, when you want to join the Polkadot ecosystem, you pretty much have to choose between either becoming a parachain or bridging with the ecosystem. And I feel there is still a lot of confusion about which path is good to take. And it all boils down to the trade-offs that you are willing to take. So if you think about parachains, this is pretty much about efficient interactions with all other parachains that are there in the ecosystem. And the analogy that I like to use here is sending a message to another parachain is as simple as sending an email. You pretty much write the stuff that you want, you click send, and it arrives on the other side of the world instantly. So you have high messaging throughput, messaging is cheap, and there is low latency between these two messages, pretty much just one block. Also, you have guarantees about the high security of this other parachain because it's also part of the same ecosystem, plugged into the same relay chain, so protected by the same shared security pool. When we think about bridges and we kind of expand this analogy, you write the thing, you write your email, but then you print it out, you put this letter into an envelope, you take that envelope, you put it into a container, then you take this container and you put it on the ship, and then that ship goes through the entire world to deliver that message. And also note that even though I mentioned container, it's actually not a very big container. It's a super tiny container that just goes on a very large ship. So the messaging throughput is much lower than in ParaChains. Messaging is also going to be expensive. We, like as we later know, we wait for finality of blocks, and it involves many, like couple of transactions on both chains before we can bridge the message or deliver the message. There's also high latency related to this finality expectations. And also the bridged chain, you don't really know exactly what security it has because it's not part of the same proof of stake consensus. Despite all of these maybe pessimistic outlooks for bridges, there is still a huge need for that. And there is still a reason why we build bridges, because some of the chains are not really either capable of becoming parachains or are not willing to trade off their consensus. So let me tell you a little bit more of what we mean by bridges when we say that word. If we look from a like 100-foot bird view on what the bridge is, it's actually about two independent chains that should learn about events that happen on each other. Usually when we think about bridges at Parity, we try to kind of split it into unidirectional bridges. So you always have the source chain, so the source of the events, and then you have a target chain that should be made aware of that event. So the target chain is interested of, did this event actually happen on the source chain? And the bridge is there to actually say that it happened. And you can imagine a whole spectrum of bridges where someone just says, hey, yeah, this happened, just trust me. Or we can go to the other side of the spectrum where we have trustless bridges. And in that case, a way to tell target chain about this event is to show that target chain a cryptographic proof of that event that it will be able to verify. And if we kind of root this a little bit more into our example in the bridges that we are building, connecting substrate-based chains, when we talk about these cryptographic proofs, we usually are going to mean grandpa finality proofs. And for instance, storage proofs. So this on-chain Merkle, on-chain tree Merkle proofs that tell us that some things happened on the source chain. And the bridge that we are building here is capable of sending arbitrary messages in both directions between these two chains. Let me hand over to Hernando right now to dive a little bit deeper into how the project is architected.
Yeah, so as you can see on the screen, we have all our code on GitHub. It's all open source and free to use, so you can find it at this Parity Bridges common repo. And really the idea behind this Parity Bridges common repo is to provide the core building blocks that we think are necessary for trustless bridges. So the first building block is a trust layer. So you need an on-chain light client which can independently verify events that happened on the source chain. The next layer is this messaging layer. You need some way to send messages across the bridge. And there's some decisions to be made here, like, do you want to support just sequential messaging? Do you want to support maybe parallel messaging? What about message acknowledgements and incentives? So there's stuff to think about here as well. Then you have this dispatch layer. So what actually happens when you get a message across the bridge? Are you going to support things like token transfers? Are you going to support arbitrary messaging? These are the types of things you need to think about when working at this layer. And finally, you need some sort of application layer which is going to hide complexity from the user and allow nice, simple, easy to use cross-chain applications to be built. As far as the specifics, so as we mentioned, we're bridging substrate-based chains. So for the trust layer, we know that we're going to be working with the Grandpa consensus engine. So our on-chain light client is able to verify Grandpa finality proofs. Our messaging layer doesn't care about what type of message is inside, and it supports both sequential and parallel delivery. And it also supports acknowledgements. And this is important when incentivizing messages and doing payments, which we'll talk about a little later. As far as the contents of the actual messages themselves, we also don't care about that. We can say, Substrate is the super generic, flexible framework, and we didn't want to get in the way of that flexibility. So we wanted to be able to dispatch any sort of Substrate call that you could think of. And as far as the application goes, well, we haven't really built any because we're not the experts at building applications, we're the experts at building infrastructure. And that's why we're here presenting this to you. We're hoping that you guys can go out and build some nice user-friendly applications that work with bridges. So cool, we have these pallets, we've implemented them into our chain. So how do we actually get events from the source chain to the target chain? One way to do this is to sit on Polkadot.js apps and listen for new events that happen on the source chain, like a new finalized header, a new message, scale and code them yourselves, and then submit them as a transaction to the target chain. After the 100th header or so, this gets really tiring. So as part of the Parity Bridges common repo, we have this external component that we built called the bridge relayer. And the bridge relayer is standalone. It automatically subscribes to events on the source chain and relays them to the target chain. A couple cool things about the bridge relayer. One, it's not staked or bonded as in a lot of other bridges. This means that you can go on GitHub, grab a binary, and run a bridge yourself. At the same time, you can also just build your own bridge. Maybe you don't like the implementation we've built in Rust, so you want to build one in Go. It's totally cool as well. Or you can just totally bypass the relayer and sit on Polkadot.js apps and keep submitting transactions yourself. All right, now I'm going to pass it over to Tomasz for a little bit of a UI demo.
Connected to two of our internal test networks, Rialto and Milao. And here I can select an account that will be transferring Milao tokens by sending a message to Rialto chain, so to the source chain. This particular account has Rialto tokens, but it doesn't really have any Milao tokens in. Since we are transferring across the bridge, we need to select an account that actually holds a bunch of Milao tokens as well. So this account here, Charlie, it has a companion account that is holding Milao tokens on the Milao chain. I'm going to send some tokens to an account that is coming from my Polkadot.js extension. And this address is not really recognized by UI. So it's neither a Rialto address nor Milao address. So the UI doesn't really know how to treat it. Am I going to use this address on Rialto or rather on Milao as a private key? So here I need to select which account I am interested in to receive the tokens. And I'm going to select native to receive tokens directly to the address as if I was a Milao chain user. So I'm going to send the 7 Milao tokens right now. And below this UI, you can see that we are waiting for all of the steps required for this transfer to actually happen. So first, we are going to wait for this transaction to be included on Rialto chain. And now the message is queued to be transferred across the bridge. Secondly, we are waiting for block finality on Rialto so that we know that this message is not going to be. We'll wait for the relayer to actually pick up this block, this final block, and deliver a cryptographic proof to Milao chain that this block is actually finalized on Rialto already. This will establish our trust layer, which Hernando will go into more deeper in the next slides. And OK, we have the block relayed right now, and now we are waiting for the message delivery. So we are jumping on the second layer right now, and we can see that the relayer did deliver the message, and you can see that the balance actually got updated on the Milao chain. Cool. These two last steps are optional, and this is about delivering a confirmation back to the source chain, so back to Rialto, that this transfer actually did happen, did occur. And this is also a cryptographic proof that this thing happened on the target chain. Cool. Let's wait a few more seconds, and we should see that it did work. Yeah. Okay. Cool. We got it. Let me see my slides now. All right. So now what was happening in the UI was we were selecting an account on the source chain. So the account that we are going to interact with, so the private key that we are going to use on the source chain. But every account on the source chain has a companion account on the target chain that is able to hold target chain tokens. So in our bridge design, we are not really transferring the tokens across the bridge. So the tokens stay on the chain where they originate on. We are just transferring an intent to transfer tokens. And this companion account is kind of like a puppet that you control by sending this bridge messages. So let's go into the example here. So we have Alice on the Kusama chain holding some Kusama tokens, and she's queuing up a bridge message to transfer some dots to Bob. Bob is actually a native Polkadot user, so he's using his private key and he interacts with the Polkadot chain. And what happens is the bridge is delivering the message to Polkadot by establishing this trust layer, then by going in this messaging layer. And when the message is dispatched, we transfer 5 dots from Alice's companion account to Bob's account. Okay. This is because, as we said earlier, our bridge is dealing with arbitrary messages, and a token transfer between these two chains can be easily implemented on top of that. Another use case is where both Alice and Bob are actually Kusama users. So if you paste an account address that is actually a Kusama address, the UI will recognize this. And instead of creating a transfer directly to like Bob account ID, it will create a transfer to Bob's companion account. So again, the bridge is delivering the message to Polkadot, and then you can see that the transfer happens from the Puppet account of Alice to Puppet account of Bob. So for Bob to spend these funds, he has to send a Kusama transaction now that will be sent across the bridge to the other side. Cool. Let me hand over to Hernando now again to do a little bit deep dive into our components.
Yeah, cool. So first, we're going to start off with this trust layer. So again, an on-chain like client. And really how this works is that, so actually, let me give you a little bit of background for what's going on. So we have 2 chains now. We're not calling them source and target anymore. It's going to be this template chain and the Malau chain. The Malau chain is an internal test network that we have. And the template chain is a chain which we'll be using for the demo in a little bit, which is based off the Substrate node template. And our goal here is going to be to convince the Malau chain that an event happened on the template chain. And how we do that is whenever there's a block that's been finalized on the template chain, we can get a grandpa justification, so finality proof for that, and submit that over to the Malau chain. The on-chain light client on the Malau chain can then verify signatures and check that the right grandpa authority set signed off on this. So a little bit, more details on how this works. So let's say that we just started our bridge. The Malau chain doesn't know about anything that's happened in the template chain. The bridge relayer will see, though, that the best finalized block on the template chain is block 3. So it'll grab that along with a grandpa justification, so again, a finality proof for this block, and submit that over to the Malau chain. The Malau chain will use this on-chain light client to verify that, yes, block 3 was indeed finalized, and then other layers such as messaging or token transfers can now happen. There's this economic guarantee that block 3 won't be reverted on the template chain. So let me jump into a little bit of a code that's required to actually implement this. So the first thing I want to show you guys is the pallet. So the pallet we have is pretty simple. It's only got one main entry point, which is a submit finality proof dispatchable. And it takes two things: the finality target, so the header that we're interested in, and a proof that this header was indeed finalized on the source chain. If I jump over to the Malau runtime, I can see that implementing this pallet for my runtime is quite easy. So I say, like, the main thing we need to worry about here is the type of chain that we're bridging. And here, what this does is it indicates to the Malau chain, I want to bridge to the template chain. I want to use this type of header, this type of hashing algorithm, and that sort of thing. Another thing you might notice if we look up here is that we can also bridge all sorts of different chains. And this is because the bridge palette we've built is instantiable. So in this case, we can also get headers from West End, and we can get headers from Rialto, which is another internal test network that we have, and verify the finality of those. We also have the relayer. So there's some code to hook up the relayer so it can submit these headers on its own, but I'm not going to show that now because that's a lot of code and there's not enough time. So let me jump into my terminal. So I just want to show headers from the template chain being verified on the Malau chain. So first I'm going to start a template node and a Malau node. Don't worry if you can't see the logs here. It's not that important, and I'll blow up what is important. So first we want to wait for finality of a block on the template chain. So let's give it a second. Okay, so we finalized one block. This is good. And now I'm going to start the relayer. So the relayer is going to send headers from the template chain to the Malau chain. So the first thing it's going to do, it's going to initialize the bridge. So it's going to submit an initial header. It doesn't necessarily have to be the Genesis header. Because for instance, maybe you're syncing Kusama, and you don't want to sync all the headers from Genesis to now. You just care about the current block and onward. Once it's initialized the bridge, it'll actually start submitting headers to the Malau chain. And you can see that it's tracking the progress of the template chain. If we hop over here to the Malau chain, you can see that we've tried to import a header, and we managed to successfully verify and import it. So this means that the Malau chain is following the progress of the template chain automatically. There's no central authority here. There's no magic, just code. All right, let's hop back to the slides. Okay, so you've seen the finality sync in action. So now you might ask, well, how much does this cost to use? From a user's point of view, this is totally free. And this is because as a user, you'll never be interacting with this directly. You'll be interacting with the bridge at a much higher level, such as at the application level. What about for the relayer? For the relayer, the cost is low, but there is a cost. So the cost is as a relayer, we need to run a source chain node and a target chain node. Additionally, we need to run the relayer application. We also need to consider the transaction costs when we submit these new headers or events to the target chain. So the relayer is going to have to pay for those out of pocket. We also decided not to have incentivization at this layer. And this is because we figured this layer was so important that anybody building cross-chain applications would be incentivized to run this layer anyways. If you've got a cross-chain DEX, if the header sync or finality sync isn't running, your application's not going to run. So you are incentivized to run this regardless of whether or not you get paid. All right, I'm going to hand it off to Tomasz now to talk about the next layers in the stack.
Cool, thank you. So Hernando mentioned the trust layer, so the on-chain light client. And actually, the trust layer is something that you can call a bridge already, because we know what happened on the other chain, and we can present cryptographic proofs right now to this chain that actually, yeah, a transaction was included, or some storage item is like that. On top of this, we have built this messaging pallet that allows you to queue messages and have them delivered with some guarantees on the other chain. So this is a picture that is kind of giving you an analogy of how our particular messaging palette works. So we have a bridge between Kusama and Polkadot, and on this bridge you can see a road. This road has multiple lanes going into one direction and multiple lanes going on the other direction. There are cars which represent messages that are being delivered to the other chain. And as you may expect, cars that are on the same lane on the road, they need to arrive on the other end exactly in the same order as when they were sent. So we have like this sequential guarantee for messages that are being sent within the same lane. However, messages that are on different lanes can be delivered in arbitrary order. So we don't define the ordering between multiple lanes. Cool. How this thing works and what the relayer is doing under the hood. So the relayer is responsible for a single lane. And what you can do on the source chain, in that case, the template chain that Hernando mentioned, you can queue messages to this pallet and have them wait and to be delivered to the target chain. The relayer is then, the target chain holds a state or an inbound lane, something that is called an inbound lane, and this contains the next message that it expects to deliver, or actually the last delivered message. So here we have the relayer creating a transaction to Milao chain containing these two messages that the target chain doesn't know about yet. So these messages are being sent alongside with a cryptographic proof that they are part of the template chain storage. And the messaging layer is based on the trust layer. So we can verify that this cryptographic proof is correct by simply checking the latest final header. When these messages are delivered and dispatched, obviously on Milao, the pallet updates the next or the last received message that it got from the relayer. And the second thing that we've mentioned is that we now we now have the side effects that happened on the Milao chain, but the template chain doesn't really know what happened with these messages. Were they delivered or were they not? So the relayer is sending another transaction, presenting a proof of the inbound lane state and showing the template chain, the source chain, that these messages have indeed been delivered, and we actually also know the dispatch status of these messages. So we know if they succeeded or failed. What the template chain is doing, it's actually removing these messages from this on-chain queue, and then it's distributing rewards to the relayers that were responsible for delivering these messages. So let's look at the incentives right now. So this is something that might already be used by a user. Of course, the user can be using something that is on the application layer, but this allows users to send arbitrary messages already. And the user has to cover all of the fees that are necessary to offset the costs of the relayer. So the user is paying first for queuing up the message on the source chain. Then it's paying for the delivery and dispatch cost on the target chain of the message that they want to send. And it's also paying for delivery confirmation transaction that the relayer has to send back to the source chain. On top of this, there is a fixed relayer reward that we charge users to compensate the relayers for the cost and the risk that they have. because notice that the user is a source chain user. So whatever he or she is paying for happens on the source chain, and we deduct that from their source chain account. So it means he's paying for all of these costs in source chain tokens, despite the relayer actually needing to send transactions on the target chain. So we rely on a price oracle here to know what is the rough cost of these or exchange rate between these two tokens, so that we know how much the user should pay, kind of like minimally pay to make sure that the relayers are interested in that message. We have a PR pending to reduce the reliance on this oracle by paying the dispatch costs on the target chain, actually. And we hope that this will be merged and deployed on the live network before we go live. And the relayer is obviously paying for the fixed kind of standby cost. Then they have this delivery and dispatch costs on the target chain and the confirmation costs on the source chain. However, there is a bunch of bundling opportunities for the relayers here, which also increases their reward on top of this fixed reward that we have. So the relayer can take multiple messages and can deliver them in a single transaction to the target chain. Same with delivery confirmations. So many messages can be confirmed at once in one transaction. And now let me tell you how to integrate your this messaging palette into your runtime. I'm not going to do a live demo because there is like a little bit more code involved in this than for the header sync. But just to kind of give you a gist of what is needed. So we need to specify what chain are we bridging with. So what is the target chain, so that we can calculate the fees correctly. Then we can control with this lane messages verifier, we can control what are the rules and filters for messages that can be sent over a particular lane. So for instance, on one lane, we can only enable balance transfers, or we can only allow calls to a particular pallet on the target chain. Then we need to indicate how the rewards are going to be paid. And we have a simple instant currency payments plugged in here. So pretty much whenever the relayer confirms the transaction, the payment for that transaction is going to be instantaneous. However, it's very easy to change it to a different scheme where, for instance, we reward relayers and then let them withdraw in the future. From the receiving side of the bridge, so the thing that is processed on the target chain, we need to know which chain is sending us the messages and how we can verify correctness of these messages, so how we can verify these cryptographic proofs. And then we need to tell the pallet how to dispatch this message. So this is this third layer that we've mentioned. And right now, the dispatch mechanism that we have implemented, as Hernando mentioned earlier, this is arbitrary scale encoded calls of the target chain. Cool. What is needed for you to kind of follow this workshop further is to add messages palette to the Milao runtime, then add messages palette to the template runtime, because this palette has to be added to both chains. Then you need to let the relayer know that there is these two chains that can be bridged together so that you can easily run the binary. You have to run both networks, and then you have to run the finality relayer and the messaging relayer so that these two layers can work in unison. Yeah, let me hand over to Hernando again to tell you more about our road to production.
Yeah, before I get into that, I do want to say that the code that we're showing here for this workshop is available on GitHub. It's in the Parity Bridges common repo under a branch called HC Clean Workshop. And that takes you from, a Substrate node template to, bridging that to the Milao chain, with message passing and all that. So now let's talk about the road to production, which is long and filled with optimistic deadlines. Nevertheless, we are at a pretty good state. So All the pallets that we've shown you today are basically ready. They've gone through a first round of audits, but we do need to go through a second round of audits since there have been some changes since the last audit. But they're ready. You can plug them into any standalone Substrate chain today and start bridging them. And you can bridge other chains without them knowing. So like I was showing in the Malau chain that we had West End there, West End had no idea we were bridging it, right? But we were able to follow its consensus. So you can go ahead and do that today. We're also in the middle of deploying a Rococo to Wococo bridge. And for those of you that don't know, Wococo is Rococo's evil twin, which is, if you're testing a bridge, you need two networks, right? So we need to spin up a clone of Rococo so we could test the bridges. And there was actually a runtime upgrade earlier today, and now both the header sync pallets are available on both of those networks. So over the next couple of days, we're going to go ahead and get that going. And then we've also finalized at least the initial UI design. We can send tokens across the bridge in a pretty nice and easy to follow way. I'm going to let Tomasz take it for next steps.
So yeah, as Hernando mentioned, after successful Rococo and Wococo launch, after re-auditing, we hope to prepare a proposal to bridge Kusama and Polkadot and to enable that that functionality that we have shown today. We still need to implement a different trust layer if we want to bridge with parachains. But since we have this layered architecture in our design, the trust layer is the only thing that we need to change to make this happen. So pretty much we change how we verify grandpa finality proofs to work with parachains. Then we want to provide way more ecosystem integration examples. For instance, how to send an XCM that is later sending a message across the bridge, or how can you implement this token transfer or token teleporting between the bridge. And something that I'm really the most excited about is changing the dispatch layer from arbitrary scale encoded calls of the target chain to actually XCM payloads. So what this will enable is you have the same messaging format between parachains and between bridges. So you will be able to send a message that starts at a parachain at Kusama, then goes to a bridge parachain on Kusama, then goes across the bridge to a bridge parachain on Polkadot, and from that bridge parachain on Polkadot goes to yet another parachain on Polkadot network. So I think this will be super interesting, and I'm really excited to see this happening soon. And that's pretty much all what we have for you today, folks, and we are happy to answer any questions.
Thank you both very much. Let's see what we got here in the chat. I know there was a couple people, friends and family, asking some questions in there as well. Here's one from Chevdor. So this was 18 minutes ago. So where in your talk was 18 minutes ago? I'm not sure. So is a given dot in both the main account and the Puppet account, and there's no risk to spend on both chains, or is it dot either in the main or the Puppet account?
You want to answer that, Hernando, or should I take this one?
You can take it.
Okay. So yeah, as I mentioned, the tokens never really leave the chain in the example that we have shown. So as a user, you are always a source chain user. So you control your private key, you have your source chain tokens on the source chain. But what Bridge gives you is this Puppet account that you also control, but not by directly sending transactions on the target chain, so on Polkadot, but rather by sending bridge messages over the bridge by sending Kusama tokens. So it might sound like it's not super interesting, right? Because I can just use the same private key, I can go to Polkadot. But there are many cases where, for instance, this other network might not be accessible to you. Maybe you can't really send transactions on that other network. You can't connect to it directly. Or there are also entities that doesn't really have private keys, but would be interested to control a Puppet account on the other network. And you can imagine, for instance, a governance of a particular network, so Kusama governance or a Kusama treasury, controlling some puppet account on Polkadot and having dots and staking these dots and so on.
Cool. So here's another one. Do messages between chains have any kind of priority level so devs can help prioritizing critical events versus best speed ones?
So that's something that can be implemented per lane. So these lanes are independent of each other, and we can control what kind of messages can be sent over a particular lane. So if we have some critical messages, then we can have a permissioned lane that, for instance, only a root origin on the source chain can queue messages to. And this will be used for a priority delivery. Like within a lane, we don't really have any priorities because there is this like sequential ordering of messages. And also like across multiple lanes. So I said that they all can be delivered in parallel, but depending on the relayer configuration, what you have to do is like you have to pay a little bit more on the target chain for these transactions to be included earlier. So in case of substrate-based chains, you need to include a tip for the miner if you want some transactions to go faster on the target chain. And obviously, this is regular transactions. Even like this is possible to implement a little bit more kind of prioritized bridge execution, but we didn't consider this yet. And right now, you are when you are a relayer, you are not kind of permissioned or treated specially on the target chain. So you are just a regular user sending transactions, and these transactions happen to be calling the bridge pallet and providing the cryptographic proofs of messages on the source chain.
Cool. I know we don't like to give dates or specific timelines for software development, but people are interested in knowing how far off the Kusama Polkadot bridge might be.
Yeah, it's hard to tell because, so as I said, there are a few different steps that need to happen. So first, we need to fully deploy on Rococo and Wococo. If that goes well, we still need to go through another round of audits. So that can be, I'm not sure how long. Then we need to like fix all these issues, and there's a bunch of different things that have to happen. Yeah, I'm not brave enough to put a date on it. Maybe Tomasz is.
Yeah, I hope it's going to happen really soon, and I'm really positive because we have spent the last year working and polishing this. There's a few things that, as Hernando mentioned, we want to make as secure as possible. Because like the thing is that for the bridge to work, you need two networks, right? So we can't deploy on one testnet and say, oh yeah, it's running. We actually need two testnets. Then we have Kusama as a chaos net. Sure, we could deploy to Kusama, but then what do we bridge with? We pretty much need another chaos net that we can bridge to if there is some chaos to be expected. But we are going to bridge with Polkadot, so it means we have to apply a little bit stricter security processes to get that done. But yeah, I really hope it's going to happen rather within weeks than months.
Expect chaos. It's literally in the name. One or two other questions here before we wrap up. I don't know if you mentioned this in the talk. People are asking what kind of documentation or if there's a wiki on companion accounts and the rest of what you spoke about other than in the Git code.
It's mainly in the code. At the end of the day, the code is the truth. But we do have some like high-level diagrams and visuals somewhere in the repo. I think if you go to the README and read through, we do link to those things. And also within the code, there's actually some good documentation. So there's READMEs alongside components like the message lanes, and those go like very into depth as to like what's happening. Yeah, we also do have a couple other talks, like we gave one at Substrate Seminar a couple of weeks ago. If you want to see one that, something longer than 35 minutes or 45 minutes. So there are some resources on the internet that you can go to.
Appreciate your time today. Thanks for speaking with us here at Decoded.
Yeah, thanks. This was fun.
For having us.